In this next problem, we have an object that's on an inclined plane. This inclined plane is tilted at an angle of 30 degrees, and the coefficient of kinetic friction on the ramp is 0.25. So the first thing that we need to do is calculate the weight of this box. So we go through, the weight of the box is going to be 25 kilograms times 9.8 meters per second squared, and that gives a weight of 245 newtons. The next thing to do is to break the weight of the box into components. We break it into a component that's perpendicular to the ramp, and we break it into a component that's parallel to the ramp. Again, this is the right angle. This angle right here is 30 degrees. It's the same as the angle of the incline. Unlike the problems where there was no friction and all we really needed to find was the parallel component of the weight, in this problem we need to find both because the normal force is going to depend on the perpendicular component of the weight, and the force of kinetic friction will depend on the normal force. So the parallel component of the weight will be 245 newtons times the sine of 30 degrees, which is 122.5 newtons. The perpendicular component of the weight is 245 newtons times the cosine of 30 degrees, which is 212.176 newtons. The other forces that we have acting on this box are the friction on the box, and this box was released from rest and it slides down the ramp. So since it's moving down the ramp, that means that the force of kinetic friction is acting up the ramp, opposing the direction that the object is sliding. The other force that we have acting on the box is the normal force. And because there are no other forces acting perpendicular to the ramp other than the perpendicular component of the weight, this means that the normal force is going to equal 212.176 newtons. This box is going to not only have its velocity down the ramp, but the acceleration is also going to be down the ramp. And so I'm going to set this up so that down the ramp is the positive direction. The first part asks us to find the magnitude of the frictional force acting on this box. The force of kinetic friction equals the coefficient of kinetic friction times the normal force, which means that the force of kinetic friction is this coefficient of kinetic friction, 0.25, times the normal force of 212.176 newtons. And so the force of kinetic friction is 53.04 newtons. Now, looking at this, we have a force of 122.5 newtons that's acting down the ramp, and we have a force of 53.04 newtons that's acting up the ramp. Those two forces together are going to be our net force acting on this box. So as we go to try and find the acceleration of the box as it slides to the bottom of the ramp, we need to find the net force on the box. The net force is the individual forces added together. And so the force that's acting down the ramp, which we were calling the positive parallel direction was the parallel component of the weight, which is 122.5 newtons, plus the force of friction. But the force of friction is acting up the ramp in the negative parallel direction, so it's negative 53.04 newtons. And so putting those two things together, 122.5 minus 53.04 is 69.456 newtons. We also know that the net force on the box equals the mass of the box, 25 kilograms, times the unknown acceleration of the box. And so if we take those two things and put them together, we have 69.456 newtons equals 25 kilograms times the unknown acceleration A. And so this gives us an acceleration down the ramp of 2.778 meters per second squared. Again, in these problems of the object on an incline, you need to be careful that you're finding the correct normal force. The force of friction is the coefficient of friction times the normal force, which is not always just equal to the weight of the object. So you go through, you find the force of friction, and then it's just going through and accounting for all of the forces that are acting on the box to find the net force and seeing what the acceleration due to that net force is. In this next problem, there's a 34 kilogram box that's resting in the back of a pickup truck. The truck is traveling at a speed of 15 meters per second, and then the truck hits the brakes. Now, if there was no friction, the box, because it has inertia, was in motion, and so it would want to stay in motion. The truck would be slowing down and stopping, but the box would continue forward. Because there's static friction, the static friction is going to keep the box from slipping, and the static friction is going to act against the direction that the box is trying to slide. So in this problem, we're told that the coefficient of static friction between the box and the truck bed is 0.357. And we're going to figure out the maximum acceleration that the truck can have without the box sliding. And if the truck comes to rest very gradually, we can see that friction would be enough to keep the box from sliding. But if the truck tries to stop very abruptly, then the friction will not be big enough and the box will slide forward. And because the force of static friction is going to be acting against the direction that the box is trying to slide, since the box is going to try and slide forward relative to the truck or to the right, this means that the force of static friction is going to be acting to the left on the box. It's the force of static friction that causes the box to slow down and stop. And so for this problem, I'm going to set it up so that the right is the positive x direction. And we need to look at the forces acting on the box. So if we look at the box, there are three forces acting on it. The first is the easiest one for everyone to see. It's the force of gravity acting on the box, 34 kilograms times 9.8 meters per second squared, which is 333.2 newtons. The only other force acting perpendicular to the truck bed is the normal force. Since the box is not moving in that perpendicular direction, that tells us that the normal force is going to have to equal 333.2 newtons as well. And then the final force that we have acting is the force of static friction. Whether or not this is at the maximum acceleration, as long as the box is not slipping, static friction is acting to the left on it. If this had a very gradual if the truck had a very gradual acceleration, then the static friction force will not be very big, and that static friction force can get bigger and bigger and bigger up to some maximum value. So again, because I was setting this up so that the right is the positive x direction, that means that the net force acting on this box is the force of static friction, but since that's acting to the left, the net force is negative F sub s. Again, F sub s, the force of static friction, that gives us how big the force of static friction is. We also know that the net force acting on the box is going to be the mass of the box, 34 kilograms, times the unknown acceleration of the box, which is going to be the same as the acceleration of the truck. And if the truck is not slipping, if the box is not slipping relative to the truck, that means that the box and the truck together have the same acceleration. So putting those two together, negative F sub s equals 34a. At the maximum acceleration, when the truck has its maximum acceleration, the reason that it's the maximum acceleration is that the box is about to slide at this point. If the box is about to slide, then that means that the static friction force is at its maximum value. Remember, the force of static friction is less than or equal to the coefficient of static friction times the normal force. So that means that the maximum value of static friction is when it's equal to the coefficient of static friction times the normal force. We have the force of static friction is at its maximum value when we have the maximum acceleration. So minus F sub s max is going to be 34 kilograms times the maximum acceleration that the box can have. And so then, taking this and plugging it in for the maximum value of static friction, we have minus the coefficient of static friction times the normal force equals 34 kilograms times the maximum acceleration. We were given that the coefficient of static friction in the problem was 0.357. And we calculated that the normal force was 333.2 newtons. So we have negative 0.357, the coefficient of static friction, times the normal force of 333.2 newtons. And that's going to equal 34 kilograms times the maximum acceleration. And so if we solve this for the maximum acceleration, we get that the maximum acceleration that the truck can have is negative 3.4986 meters per second squared. Again, this is what we were being asked to find in Part A. Part A wanted to know what is the maximum acceleration that the truck can have. Again, the maximum acceleration that the truck can have is the same as the maximum acceleration that the force of static friction can cause the box to have. So we want the maximum acceleration that the truck can have without the box sliding. So again, that was the key phrase in there, without the box sliding. Part B is asking us for the shortest distance that the box can stop in. So that's going to be using the acceleration that we found with kinematics. So the minimum distance, the shortest distance that the truck can stop in, is when the truck has its maximum acceleration. Again, sometimes that is a little bit confusing to people, but the maximum acceleration means that it's going to stop the quickest, which is stopping in the shortest distance. So you have to think these things through, because sometimes it's easy to get confused with maximum and minimum. So for this, even though we're looking at the minimum distance for the truck to stop, that's going to be when the truck has its maximum acceleration. And that maximum acceleration was what we found in Part A. So as we go to set this up, we have that the starting position is 0. We're trying to find what distance it stops in. We know that the initial velocity was 15 meters per second. We know that the final velocity is 0, because it's stopping. And the acceleration that we have is our acceleration from Part A, which is negative 3.4986 meters per second squared. And we don't know what the time is, although another variation of this problem, instead of asking what is the minimum distance for the truck to stop, they could ask what is the minimum time for the truck to stop. Again, if it stops in a time longer than that, that would be a smaller acceleration, and that would be okay. If it stops in a bigger distance than what we're going to find, that would be a smaller acceleration, so that would be okay. Static friction would be big enough. So to solve this, we're going to use the kinematic equation that relates the velocity to the position. So we have that the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement of the object. So we have 0 squared equals 15 squared plus 2 times negative 3.4986 times x minus 0. So we have 0 equals 225 minus 6.9972x. Or we get that the minimum distance to stop is going to be 32.1557 meters. Again, if the truck tried to stop in a distance shorter than that, that would be a larger acceleration than we found in Part A, and so that truck would not be, the friction between the truck and the box would not be big enough to keep the box from sliding forward. This is something that you see all the time. If you have something sitting on the seat next to you and you slam on the brakes, often the object that was sitting in the seat next to you will slide forward. But if you were to slow down gradually, then the object doesn't slide forward. And it's because friction, in that more gradual case, the static friction is big enough to keep the object from slipping off of the seat. In this problem, there's a box that's at rest on the ground, and you're going to push on the box, but you're pushing down at a 55-degree angle below the horizontal. When the force that you apply is 25 newtons, the box just starts to slide. From that, we can determine what the coefficient of static friction is between the box and the ground. So the first thing that we need to do is we need to take that applied force, the 25 newtons, and we need to break it into x and y components. This y component of the applied force is going to be 25 times the sine of 55 degrees, which is 20.4788 newtons. The x component of the applied force is going to be 25 times the cosine of 55 degrees, which is 14.3394 newtons. Another force that we have acting on the box is the force of gravity, which is 10 kilograms times 9.8 meters per second squared, which is 98 newtons. We also have the normal force acting on this box. Now this is a problem that you have to be careful. This applied force is pushing down on the box. It's pushing it harder into the ground, which means that the normal force is going to be bigger. The normal force not only needs to balance out the weight of the box, but it also needs to balance out the y component of the applied force. Again, since it's not moving up or down relative to the ground at all, the forces perpendicular to the ground must add up to equal 0. That means that if you add all of the forces that are up perpendicular to the ground, they must balance out all of the forces down perpendicular to the ground added together. In this case, there's one force that's upwards perpendicular to the ground. That's the normal force. And there are two forces that are down perpendicular to the ground. So this means that the normal force is going to equal the y component of the applied force plus the force of gravity. So it'll be 20.4788 newtons plus 98 newtons, which is 118.4788 newtons. The final force that we have acting on this box is the force of static friction. If the box is not sliding, that means that the forces parallel to the ground balance each other out. That means that the x component of the applied force is being balanced out by the force of static friction. When it was about to slide, that means that static friction was at its maximum value. This means that in this case, we know that it was about to slide when the x component of the applied force was 14.3394 newtons, and that had to equal the maximum value of static friction. So 14.3394 newtons equals, again, the maximum value of static friction is the coefficient of static friction times the normal force. And the equation we have for static friction is that the force of static friction is less than or equal to the coefficient of static friction times the normal force, or the maximum value is when it equals the coefficient of static friction times the normal force. Again, often in static friction problems, you're looking at that point when it's about to start sliding. And in those cases, you use the maximum value of static friction. If you're not told that it's about to start sliding, then you just would have gone through and looked at the relationship that we had right here, that the x component of the applied force equaled the force of static friction. If we weren't told that it was about to start sliding, all we would know is that the force of static friction would have been 14.339 newtons, but we would not have known that it was at its maximum value. Because we're told that it's about to start sliding, then this does tell us that it is at its maximum value, and so we can use this equation that we were looking at. So we have 14.3394 newtons equals the unknown coefficient of static friction times the normal force that we found above. Again, that normal force was not just the weight, but it was the weight plus the y component of the applied force, which was 118.4788 newtons. And this gives us that the coefficient of static friction between the box and the ground was 0.12103. Again, the coefficient of static friction and the coefficient of kinetic friction, those are both things that are unitless quantities. With this problem, you do need to be careful because this y component of the applied force is acting downward, so that you have two downward forces that must balance out the one upward force. And again, you're looking at that transition point from when it's not sliding to sliding. So again, when it's about to slide, you know that static friction was at its maximum value. And that's the only time that you can use the coefficient of static friction times the normal force. And if you're not told that it's about to slide, if you're not told that static friction was at its maximum value, you cannot make that assumption, and you're just looking for forces to be balanced.